Hello, everybody. So I'm Sylvain Cotard. I will be your master of ceremony for the next two sessions, or the next two presentations. Welcome for this beginning of afternoon. We will discuss safety and cybersecurity. And for the first talk, I'm pleased to introduce Brian Petersen. So Brian is an experienced expert in networking and silicon design. Since 2018, he is currently the chief architect at Eternovia, where he's leading the development of next generation of Ethernet solutions for the automotive industry. Before that, he has held a lot of positions at major companies such as Cisco, Juniper Network, as well as in several successful startups. So please welcome Brian for his talk, Enabling Resiliency in Automotive Networks for ASIL Systems.
Thank you for the introduction. Good afternoon, everybody. Thank you for attending. We're getting down to the final sessions here. I hope you find my talk thought-provoking or at least somewhat entertaining. So I'm going to be talking about resiliency and its impact on safety. I think the first order of approximation, humans cannot drive. This is certainly true for my fellow Americans. But paradoxically, we can fly. Every time you board a commercial airliner, your odds of dying in a crash are about 1 in 15 million. But every time you get into a car, your odds of dying in a crash are about 1 in 250,000. So why this huge disparity between flying and driving? One would assume that soaring through the sky in a pressurized aluminum tube at 13 kilometers above the surface of the Earth at 85% the speed of sound, where the air pressures and temperatures are too low to sustain human life, would be far more dangerous than driving. We also have meteorological conditions like thunderstorms and icing and wind shear. Now, it's true that flying is much less forgiving than driving, but there's a number of factors at play that make flying so safe. Chief among them is training. Pilots go through a lot of initial training and frequent recurrent training throughout their careers. The aircraft themselves are meticulously inspected and maintained, so the number of unairworthy aircraft flying is vanishingly low. And importantly, redundancy and resiliency are the foundations of the architectures of these aircraft. Now, same cannot be said for cars. We have over the number of years introduced a lot of safety enhancements to the cars and the infrastructure in which they operate. But we continue to have alarmingly high fatality rates. And the reason for this is the drivers themselves. Now, we in this room have very little influence over how drivers are trained or how their cars are maintained, but we do have influence over system designs. As these systems are the ones that can take the human out of the loop when necessary. But how can we be assured that these systems will be ready and available when needed? We have to anticipate failures in our system design. When we consider risk, there's a couple of factors in play here. There's the likelihood of a failure and the severity of the failure. And the overall risk is the product of these two numbers. Now, if we consider the modern turbine engine, these things are extraordinarily reliable. Now, the consequences of a failure are severe, but the odds of failure are very, very low. Indeed, these engines can operate for 300 to 1 million hours of flying without an in-flight shutdown. Worldwide, airlines are flying about 75 million hours a year. So one would wonder, why don't we see dozens or hundreds of aircraft falling out of the sky? And the reason for that is they have two engines. So that means that the odds of losing all power is the square of the odds of one engine failing. But it's not just redundant engines that keep these aircraft flying safely. They also have redundant systems, such as hydraulics. Now, this is a schematic for a typical twin-engine jetliner. You can see it has 2 engine-driven pumps, 4 electric pumps, and a ram air turbine, all of which can provide hydraulic power. We've got multiple circuits and multiple actuators, so any one system can fail, and the aircraft is still perfectly airworthy. Now, as we move closer and closer to a future where our cars can take over for drivers or drive themselves all the time, we must adopt airliner-style redundancy to ensure the availability of those systems. These systems include ADAS sensors, machine vision processing, steering, acceleration, and braking. Ethernet networks will interconnect these systems, and Ethernet must provide the redundancy foundation that these systems require. Now, if we consider a simple network such as a daisy chain, this has a couple of unusual characteristics or unfortunate characteristics. If we assume normally distributed traffic, the central links of this network are overly burdened with traffic. And if one of the links breaks, we've divided our network in two, and we've isolated systems that should be able to communicate. A star topology has better characteristics. If a link fails, only one node is isolated. Now, things get a little dicey if the central node fails, but that's a separate issue. Now, ring networks are attractive in that they're cost-effective and they're automatically resilient. Every node can communicate with every other via two different paths. And if a link fails, it reverts to being a daisy chain. Now, there are some challenges associated with ring networks to take full advantage of their topology and the promise that they have. With forwarding behaviors, fault detection, fault recovery, and when the fault does occur, how do we deal with the extra bandwidth that the surviving links have to deal with? Now, starting off the forwarding behaviors, rings are, of course, loops, and generally networks abhor loops. But if we have careful forwarding database management, a frame can enter the ring at any point, be forwarded in the appropriate direction around the ring, and removed from the ring before it makes an entire loop around the ring. Now, there's one class of traffic that does not conform to this forwarding model, and that's flooded frames. Once introduced into a ring, they will circulate forever. Now, spanning tree solves this problem by disabling one of the links, reverting our ring to a daisy chain. This is perfectly serviceable, but we have some of the negative characteristics of the daisy chain, the overburdened links, and a lot of the traffic is taking the long way around the ring. The spanning tree has a couple of characteristics that are unfortunate. Even rapid spanning tree is slow to react to topology changes. The middle links are overburdened, as I've described, and half of those frames are taking the long way around the network. Now, one solution that avoids having to use spanning tree and avoids disabling any of the links is using multiple VLANs. You could configure a series of VLANs where each VLAN omits one of the links, and each of the VLANs is one link out of phase with the others. So now you have full connectivity, you've got redundancy, and every packet can take the shortest path to its destination. The challenge with this approach, though, is that if a failure does occur, you have to do a fair number of database updates to reassociate MAC addresses with new ports and new VLANs in order to continue to forward traffic. Now, an alternative approach to this is source address filtering. Any particular node in this ring knows its own MAC address and knows the MAC address of all the things that are directly attached to it that are not other ring nodes. And what this means is that when a frame is introduced to a ring at one of these nodes, that, for example, a flooded frame, it can be forwarded in either direction around the ring, and when it makes its way back to the origin, that origin bridge can recognize the source MAC address and discard that frame. So we very simply have come up with a mechanism for protecting the ring against endless circulation. Now, if you're using this method and you're also using MAC source address learning and flooding, you have to make sure you've learned that source address before you introduce a flooded frame to the network. So at this point, we have an efficient, reliably operating ring network. How do we determine that a failure has occurred? Depending on the PHYs to report loss of link is not sufficient. You could have two PHYs on either end of a wire that are perfectly happy and perfectly ready to communicate frames, but unable to do so because the bridges that they're attached to are not providing them with any frames, because some kind of a failure has occurred in the bridge themselves. It could be a circuit failure, or it could be a corrupted configuration. What's actually required is using real frames to test the network. Now, OEM provides two standards, IEEE 802.1ag and ITOT Y-1731, both describe very similar methods for doing exactly this. In particular, the connectivity check messages use the same addressing in VLANs as normal data traffic. And this way, we're able to test the actual hardware. We're not just relying on link, we're testing the actual hardware. But we're also not just testing link partners. We're testing all the way across a network. So we're testing all the connections that the network requires, and then we're mimicking normal operation. So if these test frames stop showing up, something important has happened. Now, the receiving nodes are configured to expect these frames on a regular schedule. And if two or more of these don't show up in a row, we can raise an alarm indicating a failure has occurred. Now, these frames are not free. There's a certain amount of overhead associated with them. If we assume 300 frames per second and 912 bits per frame on the wire, 100 connections established on 2.5 gigabit per second links, and we have 5 nodes in our network, we use about 5% of the total capacity of the network. So not free, but not terrible. But the benefit of this is we can detect a fault in about 10 milliseconds. And this is less than the frame time of a video frame at 60 frames per second. So now that we've detected a fault, how do we go about recovering from it? Now, in a typical forwarding database, we have a list of MAC addresses, and each one of them is associated with a port, expressed either as a port number or a port vector. And if we have 500 entries in the database that are affected by a failure, we have to change 500 database entries to recover from the failure. Now, an important observation is that a typical bridge may have hundreds or thousands of MAC addresses, but only about 8 or 12 transmit ports. So there's a significant many-to-one relationship between addresses and forwarding behaviors. And we can take advantage of this and provide an indirection between the two, what I call a next hop. The idea here is these next hops describe forwarding behaviors. So now we're associating MAC address with forwarding behaviors, and the forwarding behaviors become associated with ports. So if there is a malfunction, you just have to change the definition of the forwarding behavior, and all the MAC addresses using that next hop immediately get new forwarding behaviors. And we can take this even further. It's possible to have a list of possible forwarding behaviors instead of just one. And by pre-gaming the possible failures, analyzing what could fail, and preparing for them in advance, you can reply rapidly to the failure. And in carrier networks, this is known as protection switching. At Ethernovia, we have this mechanism in our switches that allows us to do exactly this. Every time we process a next hop, we consult the recovery mode of the next hop. And that then dictates the forwarding behavior. So all the CPU has to do is write one value to one configuration register, and we've immediately adopted new forwarding behaviors. Now, the last thing that's of interest here is extra bandwidth burden. When we take a ring network that has well-balanced, well-loaded traffic, and we eliminate one of those links, the remaining links become overburdened. Now, there's a couple things we can do to remedy this. We could over-design the network. So rather than using 2.5 gig links, we could use 5 gig links. Or rather than having one link between pairs, we could have 2 links. Or we could degrade the system performance. So when a failure occurs, we tell the video cameras to reduce their frame rate or reduce their resolution. And neither of these solutions are ideal. Now, here's what happens if we make a minor modification to the physical topology of our network. If I add one more link that bisects our ring, we now see that only one link is moderately overloaded. So all we have to do is add one link and scale up the network slightly, and we've provided a topology that allows for full bandwidth operation, even in the event of a failure. So let's link all of this now to ASIL D requirements. Achieving ASIL D is very, very challenging, as it should be, because lives matter. And here's some of the criteria that are required for achieving ASIL D. Now, the various topologies and recovery methods that I've talked about do not address all of these, but they do address the networking aspects of redundant architectures and fault tolerance. So there's obviously a lot more to do to get to ASIL D, but having a good redundancy, resiliency story takes you a long way. Now, I've talked about a bunch of different topologies, especially rings and variations on that. There's all kinds of other ways of solving these problems. But here's some things I'd like you to take away and consider. The only hope we have of achieving airline style or airline levels of safety at Automotive is taking drivers out of the loop whenever necessary. For these systems to be relied upon, the networks that they use must be resilient. Resiliency requires redundancy, detection, and recovery. If you take any one of those three away, you do not have a resilient network. I've described one particular topology, the ring and its variant, the figure 8, but there are many other topologies that are perfectly reasonable and worth investigating. And certain hardware capabilities, such as flexible non-standard forwarding behaviors, OAM, and the protect and switching, can be very, very powerful tools in providing rapid resiliency. With that, I thank you, and I'm happy to take your questions.
Thank you very much for your presentation.
Thank you.
I think we have the first question here.
I do appreciate that you provide the knowledge and the awareness about that Ethernet operations, administration, and maintenance framework. The calculation, you have got an ORM flow on a data link, to my knowledge. So I was wondering about your calculation, how much bitrate this would be added. I thought it would be much less when indicated here.
Well, it depends on the number of connections, not just the number of links, because remember, we're not trying to test individual links in the network. We're trying to test point-to-point connections across the network. So the closer you get to the software processes and the software-hardware combinations that are talking to each other and testing those connections, the better the coverage you have for failures. Because it could be one particular forwarding behavior that's not working in a bridge, and that could be a critical failure. And so you want to test as many of those things as possible. And if you want to be able to recover rapidly, being able to recover in 10 milliseconds would be great. You need to be able to send these test frames very, very quickly. So the bandwidth consumption does become noticeable when you start to do things exhaustively like this. Now, you may be able to tune that down and still have good coverage. You have to do careful analysis to make sure you're getting the coverage that you need.
So the basic ORM toolset provides connectivity, supervision procedures, and so on, and this is more you are using than which is just standardized.
Right, and any particular node in the network can be configured to send OAM frames with addressing and VLAN associations that are of your choosing. And so you can emulate pretty much any connection through the network. And so if you're able to push this testing as far to the edges of the network as possible so that you're testing the entire paths, you get much better coverage.
Makes sense. Thank you.
You're very welcome. Other questions?
Maybe waiting for the next questions. The next speaker can come here to be prepared for this presentation. Thank you.
Okay, thank you very much.